There has been a lot of interest in grounding natural language to physical entities through visual context. While VLMs can ground linguistic instructions to visual sensory information, they often struggle with grounding non-visual attributes. Our key insight is that non-visual attribute detection can be effectively achieved by active perception guided by visual reasoning. To this end, we present a perception action API for prompting an LLM to actively detect attributes. Our framework receives a natural language instruction and an image as input. It then uses an LLM to produce a Python program that combines LLMs and VLMs with robot actions to actively reason about attributes. The API consists of an image patch class and a robot action class with methods and examples. Image patch supports open vocabulary object detection, or OVD, visual question answering, or VQA, and answering textual queries. The robot class has a list of sensors as a member variable and a set of functions to focus on the center of an image, measure weight and distance, navigate to an object, or pick and place it. The input prompt includes the API with guidelines on how to use it and a natural language query. In order to evaluate the visual reasoning capabilities of the API, we build a dataset based on Node 1 out with relative object location, size, and weight queries, and compare the perception API with OVD and VQA. On the left, OVD and VQA fail to identify the heaviest object, but the API LLM-generated code returns the correct answer. On the right, OVD and API predictions are shown with green and yellow bounding boxes. Image A shows an example of agreement between OVD and the API. B shows a mutual failure case, and C and D show cases where the API outperforms OVD. Quantitative evaluation shows that VLMs often do not possess the rudimentary reasoning capability to tackle evident weight estimation queries, as shown in Figure A. The API outperforms single OVD and VQA calls in every task, but the superlative form of an adjective has no effect in grounding. We integrate the perception action API in different AI to Thor household environments. In weight estimation, we show an example where GPT-4o agrees with our API, which correctly determines the weight of an object by picking it up and using a force torque sensor. In the distance estimation task, the robot has to identify which object is closer to its camera. We use the question which one is closer to me, followed by the objects in question. We compare GPT-4o, which yields the correct answer, with the active perception behavior invoked by our API. Quantitative evaluation shows that the perception action API performs all baselines. The API relies on exploratory behaviors given any detected object, where the other baselines may correctly recognize an object due to the quality of the simulated image. We integrate our framework into a RoboMaster EP robot with the following components. Here is the robot performing active distance estimation using our framework. In the future, we plan to extend the API by integrating more sensors and develop mechanisms that catch intermediate errors before they propagate downstream.